All right, it's your old pal, Mr. Cook, and we are working on the Unit 5 probability group work. So now we're starting up on the word problems, starting with number 7. I'll probably get through like, 9 on this video, and then we'll switch over to another video. Just kind of keep it short. So number 7, a fair coin is flipped and a spinner with the numbers 1 through 5 is spun. Find the probability of getting a heads, so that's one event, and then spinning an odd number, that's the second event. So we need to multiply these together to find the overall probability. So find the probability of getting heads, that's the first one. Excuse me. So the probability of getting heads, there's only heads and tails for your options, so that's 1 out of 2. Spinning an odd number on the 1 through 5 spinning wheel. Odd numbers would be 1 and 3 and 5, so that'd be 3 options out of the 5. So we just multiply those together, we get 3 out of 10, easy enough. Now, are the events flipping a coin and spinning the number 1 through 5 dependent or independent, and explain why? Well, these are independent, just with a brief explanation. Like the heads doesn't affect the, spinning anything they're two separate samplings, like you're either going to get a heads or a tails of the coin, and then you're going to get a 1, a 2, a 3, a 4, or a 5 on the wheel. Okay, there's no like crazy prerequisite knowledge needed here. It's just like, the coin is different from the wheel. So this is not going to affect this at all. Like nothing. It doesn't change the probability at all. So that's what makes it independent. Now, mathematically, I can show that this is true as well pretty easily too. We can just use one of our little independence formulas, like the conditional probability one, for example, where we need to show that the probability of one event, is equal to the probability of that same event given the other one. As long as it stays the same, that means that this probability is not affected by this, event happening. So if we're trying to show flipping a coin and spinning 1 through 5, like, just pick one individual element from each. So I'll pick like heads and spinning a 4 or something, So like, let's test these against each other and see if they're dependent or independent. So if I flip a coin and it lands on heads, is that the same as flipping a coin landing on heads given that I rolled a 4 on the spinner? Let's find out. So flipping a coin, getting a heads, that's a 1 out of 2. Flipping a coin, landing on heads, given that it landed on a 4, the 4 doesn't affect the landing on heads at all, so it's still just a half. So this checks out. Now, with independent events, you need to make sure to check that it's independent both ways. So, check the other one as well. So the probability that I, spin a 4, is that the same as spinning a 4 given that I landed on heads? Let's find out. Well, spinning a 4, that's one option out of the 5. And let's see if that's the same. So spinning a 4 and getting a head. So I just got a heads. I'm spinning it, and it doesn't affect it at all, so it's still a 1 out of 5 probability. Now, since these are the same for both cases, that means I can claim that these two are independent events. They don't affect the outcome of the other. Amazing, right? Okay, so that's the conditional part. Now, a little bit about this. You need to show both, okay, to prove independence, but to show dependence, you just need to show once that it fails, okay? So that's pretty nice. Now, let's do number 8 and number 9. So number 8, it looks like we've got kind of a little wild sample space there. So I'm going to give myself a little bit more space to write and maybe add this. This is where I'm going to draw my sample space. A little post-it note. Assume that the probability of the birth of a child of a particular gender is 50%. In a family with 3 children, what is the probability that 2 of the children are girls? I guess that this is kind of a controversial question when you think about like all the current social stuff that we got going on. So let's just pretend this is math world where there's only boy and girl and they're equally likely to happen. Okay, so 50%. And that's it, okay? For the context of this problem, that's all that there is. So the sample space would look something like this. The first kid would either be a boy or girl, and they'd be 50% likely for each of them. Now, a conditional probability from this would be if you have a boy, then you could maybe have another boy, so that'd be 2 boys. Or you could have a girl and you'd have a boy and a girl. Either way, like from having a boy, you still have a 50% chance of having another boy and a 50% chance of having a girl, given that you have a boy first, because the probability doesn't change. And then for the third kid, you just keep branching off, so boy and girl. And then you just do that for all of them because the probability of each individual child doesn't change. So boy and girl. And then from here, boy and girl. And you can see that even with like 2 choices, this stuff kind of like takes up space pretty quick. Now, once you make a tree diagram, it's important to also write up the intersection probabilities. Now, when I say intersection, we got to remember like the intersection formula. It looks something like this. The probability of the intersection of 2 events is equal to the probability of one of the events times the probability of the other event, given that that first event happened. So what this means is like, I take this probability and then multiply it times the conditional probability over here. And then, you can just keep multiplying the conditional probabilities together with the original one to get to the overall intersection of this. So like if I multiply 0.5 times 0.5 times 0.5 for this branch, it would give me the probability that I get a boy, and a boy, like in that order. So 0.5 times 0.5 times 0.5, a half times a half times a half is 1/8, which is 0.125. And since all of these are equally likely to happen, each one of these, the ends of each of these branches are going to be worth 0.125 as well, 1/8, because they're all equally likely to happen, and there are 8 outcomes. All right, now the likelihood of all of these happening is the same, but there are certain ways to kind of look at the probabilities and add them together to kind of like find more likelihood of something happening, even though these are all equally likely to happen. One of those cases is phrasing a question like this. In a family with 3 children like this, what's the probability that 2 of the kids are girls? So this probability isn't just going to be 0.125, because there are different ways that you can get 2 girls, right, as children. You can have a girl and then a boy and then a girl. You could have a girl and then a girl and then a boy. Or you could have a boy and then 2 girls, right? All of those situations, those are the only 3 situations, but you'll end up with 2 girls. So each of those are the individual intersections. So we have girl, boy, so girl, boy, girl, so that's one of them here. Girl, boy, so girl, boy, that's this one here. And then boy, girl, so boy, girl, this one. So if we add all those probabilities together, it'll give us the union of, what we're seeking out, which is the probability that 2 of the children are girls. So we just add them up. So it's 0.125, or 1/8, plus 0.125, plus 0.125, which gives us a grand total of 0.375. And that'll be our overall probability for that case. All right, so that's the sample space, and that's the answer for that one. Now let's do this next word problem. There are 9 red and 4 black balls in a box. If 3 balls are picked without replacement, what is the probability that at least one of them is black? So this last part of the sentence is like a giveaway that that this is going to be probably one of the cases where you can use the complement probability. Because, okay, if we draw out 3 balls from this box, here are all of the different possibilities. You could get all 3 of them black, so 3 black. That means that you have 0 red. You could also get 2 black balls and 1 red one. You could also get 1 black ball and 2 red ones. And there's one last possibility, and that's that you get 0 black balls and 3 reds. Since these are all of the different possibilities, if I added up all of those probabilities, I'd end up with a total of 1. It's certain that these 4 events will happen if I draw out 3 balls at random. So this probability says that at least one of them is black. So that counts this probability, and this probability. That's what I'm trying to solve for, this. So one way to get it, the easiest way to get it, is just to find this lone last probability, the complement, and subtract it from 1. See, watch, because if I subtract this from both sides, I end up with the following. So this equals 1 minus the probability of 0 black balls and 3 red ones. So now this becomes way easier. Instead of finding 3 individual probabilities, just find 1 and subtract it from 1, and that's my answer. So let's do that. It's 1 minus the probability of getting 3 red balls in succession. So this is without replacement, so I reach into the box, and then what's the probability that I get out a red ball first? That's 9 out of a total of, let's see, 9 and 4, so 13. So 9 out of 13 would be the first probability. Then I multiply that times the next one. So I toss out that red ball, and now there's 8 red balls remaining out of the 12 balls total in the box. Then I toss out that one, and I've got 7 red balls remaining out of the 11 in the box. So that's it. That's the 3 red balls. That's the probability of getting it. Now just use the calculator to complete it. So 1 minus 9 over 13 times 8 over 12 times 7 over 11. And then convert it to a fraction. And we've got our answer, 101 over 143. Easy enough. And I think that's pretty good to stop on this video. So that's 3 word problems. We'll get into the other ones in a second. All right, so last video coming up.